I want to start this conversation with our acid-base reactions. And here's just a list of some of the strong acids and strong bases. And when we're talking about ions, these are strong acids and strong bases because they ionize completely. They fall apart completely. But when we have something that is a poor electrolyte, that means it doesn't fall apart completely, and only maybe a small percentage of those fall apart and ionize. So that's the difference between a strong versus a weak acid or base, is how well they break down. This list of strong acids and bases, they show us which ones of these really fall apart really well. Acid-base reactions is also called a neutralization, because we're going to, with an acid and a base, we're going to make water and salt typically when we add those together. Ionic compounds are formed here, and basically with an acid and a base, if you have a strong acid or a strong base, it typically means that those are ionized really well, and they dissolve in water really well, and they're very available for interaction with other compounds. And we're going to create, with this acid-base reaction, we're going to create a water molecule which neutralizes it, and then we have a salt will also form. So here's an example of perchloric acid and sodium hydroxide. A strong acid, a strong base. We're going to do the swapping of the cation and the anion. So you can see that this is a polyatomic. Here we have hydroxide is another polyatomic. So it's important, it's helpful to, I think, identify those right away. And water, I think it's usually helpful to rewrite that as HOH or HHO. It doesn't really matter, honestly. But it's helpful to rewrite that to recognize what's happening. So we're always going to have cation is first. And so we will be able to say that's going to be H plus because we have that inferred one here. There's an inferred one here. So we know that ClO4 is a negative. We also have that sodium, which is a plus because of where it's on the periodic table, and also there's an inferred one there, OH minus. What's happening to create our water is that the H and OH are coming together to create our H2O. And then we have the sodium chloride coming together to form this NaClO4. So the reason that this chemical reaction moves forward is not because we're making a precipitate, but we're actually making water. And water is a weak electrolyte or a non-electrolyte, which means that it doesn't fall apart. This HOH group stays together as a unit. Water doesn't fall apart into H and OH ions very readily. And so this liquid water being formed, that drives the reaction to happen. So in order to predict this, it's helpful to first break all of these down like I had done previously, and then rearrange them with each other. And then you can also, if you want to, you can cancel out the spectator ions and create the net ionic equation. And basically this is a simplified version of what an acid-base reaction is. We have the acid, the base, and then we form water. The salts are, those are the spectator ions, so we don't necessarily, for the net ionic equation, worry about the salt that is left behind. Whenever we're doing acid-base reactions, if we have a strong acid or a strong base, those are going to fall apart easily. What it means to be a strong acid or a strong base is that they do fall apart and dissociate completely. So the HCl becomes H plus and Cl minus. This is different than some of the other examples we were maybe talking about, where you might have a weak electrolyte where it sort of falls apart sometimes, or maybe 10% or less falls apart. These are completely dissociated and break apart and form these strong acids because we have, for example, the hydrogen that's found on these. These are all going to form that plus H charge. And then you'll notice all of the strong bases have OHs, and those very readily fall apart to form that negative charge in solution. So when we look at neutralization between strong acids and strong bases, we have hydrochloric acid, calcium hydroxide, and we're going to generate water and calcium chloride. And this is just the reaction as we break down the ions. And we'll notice that if we actually remove the spectator ions, we'll actually get the 2 hydrogen ions, 2 hydroxide ions, make 2 waters. And we can simplify that even further by dividing all of the elements by 2, and then we have the same exact example we had before, where we have the net ionic equations, essentially H plus OH is equal to water. Next, I want to talk about weak acids and a strong base. And in this example, we have acetic acid, and it is going to be a weak acid because it falls apart maybe only 10% or less of the time. So most of the compound is in this molecular form. Some of it does fall apart once in a while, and we get something that looks like this. And so that happens very infrequently. Because it only happens infrequently, we don't write it like this when we're writing this equation out typically for the ionic equation. Because again, it isn't, most of the time, it's not in this form. This is a rare instance where it is in this form. So we don't, when we're writing the ionic equation, we do not break these apart if they're weak acids or bases. How do you know if it's a weak acid or a base? Well, it's not on this list. If it's not on this list, it's a weak acid or base, so you don't break these apart when you're making the ionic chart, the ionic equation. So you don't break these apart when you're making the ionic equation. The sodium hydroxide, however, is a strong base, so that does break apart. And you'll notice that here and here, we've broken that apart because this is strong. Here to here, that's together because it's weak. It's weak because it doesn't fall apart. So next step is, we do know that, however, this hydrogen is going to still move over and interact with that hydroxide group. And so that is what's giving us our HOH group, otherwise known as water. This sodium is still in solution. And then when these things do happen, when that does break apart, we do form that negatively charged ion at the end. And so this is our ionic equation that we've made. We can take out the sodium ions because those are really just spectator ions. And then the net ionic equation will be shown here below, where we start with this weak acid, we have a strong base, we make water, and that acetate ion. Here's an example of a strong acid with an insoluble base. So magnesium hydroxide is a solid, but if we put strong acid with it, we can generate this magnesium chloride and water. And notice that magnesium hydroxide is not written out as an ion. So this doesn't get made into an ion because it's a solid, right? So now we look at the ionic equation, you'll notice that that is still written out as a solid. We don't break those apart because under normal circumstances, it's not an ion, it's together. But that doesn't mean that hydrogen can't interact with that hydroxide group to form water, which is still what happens. So without breaking this apart in the ionic form, you can still consider these two groups and how they might interact with each other. So we know that that is going to be a group and that is going to be a group. And we can still use the same rules to understand how they're going to fall apart. We do the crisscross rule to find out that magnesium is a +2 and then the hydroxide is going to be a negative. And you can also look at your charts in the periodic table to figure that out as well. We have the HCl is a strong acid. It's on that list of strong acids and bases. So we know that that's going to dissociate completely into H plus and Cl minus. Once we have that water formed, we are going to have the chloride ions are going to form in the water. So the spectator ions are the chloride ions. So the net ionic equation is the magnesium hydroxide, which is solid, which we write as one group. We have acid atoms, that the hydrogen ions that are going to be the acid. Magnesium is going to be left over, and then we create some water. So this is the net ionic equation. That's a balanced equation for this reaction. And just want to point out too, notice that we have two hydrogen ions. So this is a +2 charge on the left side, right? The overall charge of the compounds on this side are a +2. And then this magnesium is also a +2 charge. So again, it doesn't matter what the charge is. It doesn't have to be a neutral charge on both sides of this arrow. The charge just needs to be the same. All right, so one last example here, strong acid with a weak base, and we're going to look at the molecular equation. Here we have a strong acid, hydrochloric acid, and a weak base, ammonium, and we are going to generate ammonium chloride. So this is an example where a neutralization doesn't necessarily form water. But let's look at the ionic equation. We're going to break apart the NH3 and the H+. Now, a couple things to notice. The NH3, that is weak, and anytime we have something that's weak, it stays together. If it's a weak base or a weak acid, it doesn't fall apart. So that's why we draw this out in the ionic equation form as one unit and one group. Strong acids and bases, this is a strong acid, those get broken apart into their ions. And then we are going to, if this is a base, and this other version is the acid, we know that the acid, the hydrogen, is going to attach to the base, and we're going to have these chloride ions as spectator ions. So those can then cancel out for our net ionic equation, which then is the ammonia plus the hydrogen, or the proton, is going to give us ammonium ion. And so this is the example of a strong acid and a weak base. So next I want you to think about this challenge problem and post your answer in the Blackboard space in the weekly content section. So the question is, what is the net ionic equation for the reaction of an insoluble insoluble hydroxide and a weak acid? So that kind of gives you some hints about the description of these and what you should do. So I want you to draw out here's the start of the molecular equation. Write out the ionic equation based off of the kind of hints here that you're given, and then finally the net ionic equation for this, and post that in our Blackboard space. I'd like to walk you through some of the different types of acids that you may see, that you might come across, and one of them is an acid salt, and this is basically, we have polyprotic acids, which means that there are different numbers of protons or multiple protons, and these can be neutralized in a stepwise fashion. So I'll show you in a second here, if we have an example for H2SO4, hydrogen sulfate. Notice that there are two hydrogens at the front end of this, which means that we can actually, if we interact it with potassium hydroxide, then we actually form this acid salt. So there's an acid version here with the hydrogen, and then there's the salt version with the potassium. So that is going to give us this unique thing where we can react it with one group of base, and then we can do this a second time. So that's what I mean by a stepwise neutralization. Baking soda, for example, is sodium hydrogen carbonate. So you can see that instead of potassium, we have a sodium salt the hydrogen acid and the carbonate anion. So that's what baking soda is. It's kind of a weaker acid, but it can be used as an acid kind of compound. Acid salts are going to identify the number of hydrogens still attached to the anion. And again, it can be neutralized by different amounts of base. So this one's sodium hydrogen phosphate, or otherwise, if you have sodium dihydrogen phosphate, there would be 2 hydrogens. This is an example of potassium hydrogen sulfate. If you're going to have 2 of those, right, we have dihydrogen sulfate. So some of these have common names like sodium hydrogen carbonate, otherwise known as bicarbonate or baking soda. Sometimes when we do a metathesis reaction, we're actually replacing something and forming a compound that then gives rise to a gas. And this gas can be insoluble and is released from the solution. We're going to look at some of these examples for gas formation. Examples of these would be carbon dioxide, sulfide, and or ammonia by metathesis. Hydrogen sulfide and hydrogen cyanide are some other gases that can be formed when we process these. And then we can also generate salts that are very unstable that will decompose into water, and then one of these 3 elements I listed above. So this is more common where we would do a metathesis. We generate one of these, and then after that we're going to form a gas. So you may have noticed these things forming at some point if you were looking at ammonium hydroxide. If this were to form, you may have seen bubbles in a chemical reaction. And that was actually this reaction going to completion, but it was forming a gas instead of a precipitate or a solid compound. Here is an example of a chemical reaction where a gas is formed. If we look at this, we can see that we have sodium bicarbonate, or it's this acid salt here. And what's going to happen is we'll notice that the sodium is going to interact with the iodine. So that is going to interact here and create this new compound. And then the HCO3 is going to react with the hydrogen here. And then we're going to make this new compound H2CO3. What is actually then going to happen, you'll notice that on that previous slide, we have H2CO3 is found right up here. This quickly decomposes. This doesn't last long before it falls apart into water and carbon dioxide. So that is then drawn out over here as water and carbon dioxide rather than listed as H2CO3. Another example where this would happen, we have this calcium and the chloride. We'll generate the calcium chloride here. And then we have the HCO3. There are 2 units of this, 2 of these. So we can actually, we would generate 2 of these. Carbonate is also if we do the crisscross rule, right? Calcium's a +2, carbonate's a -2. So we would have to have 2 of these. So it's the same product that's formed. This H2CO3 will decompose into these 2 compounds. One of them is a gas, and so that's what will drive the chemical reaction. What's kind of nice about these kinds of chemical reactions is if you are interested in isolating the sodium iodide or the calcium chloride salt, all you have to do is boil off the carbon dioxide or the water, and you'll have a pure compound at the end that you might want. So this is, remember these, when we have H2CO3, we will generate this breakdown product. So I want you to do the equation. I want you to run through this problem, and then we're going to talk about this at a later time. So what is the net ionic equation for the reaction HCl with potassium hydrogen carbonate? Remember, look for if anything is going to break down and fall apart in here. I want you to think about this for a second here and maybe pause it and kind of walk through these yourself first. But I want you to talk to me. I want you to think about which of the following combinations will not react. And if they do, say why they react. If they don't, say why this thing doesn't react. Okay, so I want to walk through this with you. When you actually do the equations, I'm going to show you the molecular equations here. We're going to generate sodium chloride and H2CO3. Now this should hopefully raise a flag here, the H2CO3. We know that falls apart into water and carbon dioxide. That gas formation is going to show us that this is going to be a driving force and this chemical reaction will occur. The second one, we're going to make the sodium acetate plus hydrochloric acid. And this is just, these are both soluble compounds. This is a really strong acid, which we know is going to be soluble. This is a good electrolyte. So these formation of this are just all soluble ions. And so this is just going to be, this is going to go the other way if anything. So there's no chemical reaction that's going to happen in this case. So this was the combination that was not going to react. This third one here is going to be ammonium hydroxide and barium chloride. And this one, if you remember some of those other compounds in that list, we're going to make ammonium gas and water. So this will be a driving force and push this reaction forward. And finally, potassium sulfate and hydrogen cyanide. Hydrogen cyanide is a gas, and that's going to be a driving force for this combination as well. So the only combination that was not going to go forward was B, and because these are ions that stay in solution, and they won't, this won't drive the reaction forward. We can utilize metathesis reactions to synthesize different types of salts, and we really ultimately want to have our final compound should be easily separated from the reaction mixture. So however we want to do that, we want to make sure that we can use the metathesis synthesis reactions to create something that can be separated out fairly easily. We want preferably uncontaminated by other reactants or starting materials, and then we want to make sure that we are going to have either an insoluble compound in water or soluble in water, and the thing that we're going to get rid of is going to be insoluble. Here's an example where a desired compound is insoluble in water. So we start with two soluble reactants, and we can isolate this product by filtration. So if we start this, we add them together, we get that precipitate, then we can just filter out this desired product. An example might be magnesium iodide, potassium carbonate. These are both aqueous starting materials, and then we would mix those together, and we would form that magnesium carbonate. That's the cloudy substance in here. The potassium iodide, those are just those are spectator ions. They're not going to be involved, and we can easily filter those out. Another example is looking at a desired compound soluble in water. If it's gas, we can collect the gas and isolate that out, and then after we could evaporate the water and just get the salt out. An example might be sodium hydrogen carbonate or baking soda plus hydrogen iodide, and we're going to do that mixture is going to create this sodium iodide, and then we're going to create that H2CO3, which remember falls apart into water and carbon dioxide. So we'll be left just with that sodium iodide. So I want you to take a second to think about how would we synthesize something like nickel sulfate. And I don't want you, obviously you can't use nickel or nickel sulfate as your starting point. So think of something that would be soluble. So you need to make sure that we find something that is starting point is soluble. Nickel sulfate itself is soluble in water. So think about different methods where we might be able to synthesize this and purify this out using some of our what we know about the solubility rules and metathesis reactions that we talked about. So bring your thoughts to class, and then we'll talk about some of the solutions for this problem. And one more question here. If you would like to try this one, we can talk about this as well, just as a practice problem. But if we didn't have NH4NO3 because it was on back order, but we did have a lot of other chemicals besides that, what could we use to synthesize this? How would we go about doing that? So try this one out, bring your answers and suggestions to class, and we'll talk through this.